Alright, so we'll continue with section 9.1, which is conics and calculus, or conic sections with ellipses, parabolas, and hyperbolas. So here's the ellipse section. As always, if I'm going too fast, just pause the video and make sure you copy down what we got here. So an ellipse, hopefully you learned about before, it's the set of all points x, y, the sum of whose distances from two distinct fixed points or foci is constant. So it looks kind of like this, where there's two foci here and the sum of their distances together is constant. So like if you took a rubber band and put it around both of those points, it would always be the same sum, no matter where it was. So the length of the string or the length of the rubber band would be the same the whole time. The standard form of the equation of an ellipse with a horizontal major axis, like the one that I just drew going horizontally, is what you see there. So go ahead and copy that down. Hopefully it looks familiar from pre-calculus or algebra 2 maybe. And then vice versa, the standard form of an ellipse with a vertical major axis going straight up and down looks like that. So go ahead and copy that down as well. You'll notice that the only difference is that the horizontal axis, A is always greater than B. So for the horizontal axis, it will have the bigger number underneath x, and since that is the bigger number on the x-axis, and y will have the smaller number, vice versa on the vertical axis, the bigger number will be under y, and the smaller number will be under x. So that's the only thing that's different about the equations. It says in both cases the foci lie on the major axis c units from the center, with c squared equal to a squared minus b squared. So that's how you can figure out what c would be. So here's an example. It says sketch the ellipse given by 4x squared plus 25y squared equals 100. Well, we know that the standard form of the equation has a 1 over here on the right-hand side, so I have to divide everything by 100. So I get x squared over 25 plus y squared over 4 equals 1. So a squared is 5, so that's why I go out to 5 here, and I go out to 5 here on the x-axis. And b squared is equal to 4, so that's 2. A squared is equal to 25, so a is 5. And b squared is equal to 4, so a is 2. So here's 5 and 5 on the x-axis, and 2 on the y-axis, and then you just connect them using the best ellipse that you possibly can. And that's how you sketch one. It says, let P be a point on an ellipse. The reflective property of an ellipse states that the tangent line to the ellipse at point P makes equal angles with all lines through point P and the foci. And the eccentricity, that word eccentricity, measures the ovalness of an ellipse, so how oval it is. It's given by the ratio E equals C over A. It says for an elongated ellipse, the longer the ellipse is, the value of E is close to 1. And for every ellipse, the value of E lies in between 0 and 1. So the closer it is to 1, the longer it is. The closer it is to 0, the more like of a circle, so the more round that it would be. Hyperbolas. Hyperbolas are the set of all points x, y for which the absolute value of the difference between the distances from the two fixed points foci is constant. And the line through a hyperbola's two foci intersects the hyperbola at 2 points called vertices. And the midpoint of a hyperbola's transverse axis is the center of the hyperbola. So you don't actually graph it, but it is there. The standard form of a hyperbola that has a horizontal transverse axis is this one. And here's the standard form, the second one down here is the standard form if it has a vertical transverse axis. You'll notice that the only thing that switched was the x minus k and x minus h and the y minus k. So the minus sign has to stay in that order where you actually switch the entire top part of it. If we keep going, we get that a, b, and c are related by b squared equals c squared minus a squared. To figure out where the foci are located, you can use that. And the asymptotes of a hyperbola are here. Y equals k plus b over a times x minus h, and y equals k minus b over a times x minus h. I know that it's covered up down here. It says scanned by cam scanner. So if I can help you guys fill that in really quick. It says the asymptotes of a hyperbola with a vertical transverse axis are this one. And notice that the only thing that switched from here to here was the b minus a. B over a, I'm sorry. So it's actually going to be the same thing here. So the one that's covered up is the exact same thing as this. The only thing that's different is that this is not b over a, it's a over b. So you can write that down where it's covered up. Alright, and last but not least, sketch the graph of a hyperbola given the equation. So y squared minus 9x squared equals 9. So again, that's supposed to be a 1 over there on the right hand side, so I can divide everything by a 9. And y squared over 9 minus x squared over 1 equals 1. So therefore, a must be 3. So you can go up to 3 and down to 3 on the y-axis since it's underneath y. And x must have a b down here, which is 1, so you can go left and right 1. You can create this little box. And notice that the hyperbolas go through the diagonals of the box. But, I'm sorry, not the hyperbolas, the asymptotes go through the diagonals of the box. So you can get y equals 3x for one asymptote and y equals negative 3x for the other. And last but not least, the eccentricity of a hyperbola is given by the equation E equals c over a, where the values of E are greater than 1. So, let's get started on some examples. So, go ahead and open up your book. The first example we're going to look at is example 3 on page 641. So, let's look at that one. Alright, so this example gives you this equation up here at the top, and it says to find the center, vertices, and foci. So in order to do that, it would be very helpful to have this in standard form. So we're going to have to complete the square in order to put it into standard form. So I see a 4x squared and an 8x, negative 8x. I'm going to group those together and factor out a 4. So I have 4 times x squared minus 2x, and then I'm going to put a little plus blank here. And then for the y squared and 4y, I have plus y squared plus 4y plus blank. And then I can move that negative 8 over to the other side and make it a positive 8. So if I fill in the blanks, I get 4 times x minus 2x plus 2 divided by 2 is 1, squared is 1, plus y squared plus 4y plus 4 divided by 2 is 2, squared is 4. And then if I add those things on the other side, I have 8. And then this 1 is actually times 4 here, so that's plus 4. And then this 4 is not times anything, so that's just plus 4 again. So this is 4 times x minus 1 squared plus y plus 2 squared equals 8 plus 4, that's 16. And remember, this is supposed to be a 1 over here, so let's divide everything by 16. So I get x minus 1 squared over 4 plus y plus 2 squared over 16 equals 1. So now this is in standard form, and it's much, much easier to work with when that's in standard form. So, we know that this is a taller or an elongated ellipse vertically, so it's on the vertical axis because there's a bigger number under the y term. So we know that because 16 is bigger than 4, it's going to be longer on the vertical. So let's list off a couple things we know. We know that h equals 1. We know that k equals negative 2. We know that a equals 2, because that's 2 squared would be 4. And we know that b equals 4, because 4 squared is 16. So if we use our little formula for what c is, we know that c would be equal to the square root of 16 minus 4, which is equal to 2 square root of 3. So remember that formula for c that we got from our notes earlier. So I'll write that one down just so that you guys remember. It says c squared, I'll write it in red. It's the one that was c squared equals a squared minus b squared. So we just use that formula here and then take the square root of both sides. So, given all of this information, we can conclude a couple things. So let me erase some of this stuff up here so we have room. Alright, so the first thing we can conclude is that the center is at 1, negative 2, because that's h, k. We know that the vertices are at 1, negative 6 and 1, 2. because those are at h comma k plus or minus a. And we know that the foci are at 1 comma negative 2 minus 2 root 3 and 1 comma negative 2 plus 2 root 3. And again, we know that because those are at h comma k plus or minus c. So that's the center, the vertices, and the foci of an ellipse. Let's skip over example 4. So we're going to skip the orbit of the moon problem. And we're actually going to go straight to example number 5. So let's look at that one on page 643. Alright, so this one says to show that the circumference of the equation up here, x squared over a squared plus y squared over b squared equals 1, is this little thingamajigger they gave us here. So, first thing it's important to note is that notice that there's no h being added to x and there's no k being added or subtracted to y, which means that this ellipse is centered at the origin. So it's symmetrical about the x and the y-axis. So if you think about an ellipse that's symmetrical about the x and the y-axis, if you can find out whatever this length is here, then you can just multiply it times 4 to get the entire thing all the way around because it's symmetric. So we're only going to worry about the arc length of this first piece here, and then all the rest of it will fall into place from there in order to find the circumference, that is. So what we know is that the circumference is 4 times the arc length of y equals b over a square root of a squared minus x squared. Alright, and in case you're wondering where they got that, I've done a little work over here. So if you look over there, if you start with the original equation that they gave you up at the top and subtract the x squared over a squared to the other side, then you can get like terms. So if you make 1 into a squared over a squared, you can combine those so you get a squared minus x squared over a squared. Then you multiply the b squared over to the other side like I did here. And then you take the square root of both the sides to get rid of that square root over y, or to get rid of that squared over y. And then the b squared over a squared comes out as b over a, I'm sorry. So that's how they got the equation that they're looking at here. Just a little FYI. Alright, so let's keep going. So we know that we're trying to find the arc length of that in the first quadrant, and that it would be 4 times that. So the function y is differentiable for all x in the interval, except at x equals a, obviously, because you'd have 0 on the bottom of that fraction. So therefore, the circumference is given by the following improper integral. So the circumference, oops, that's not the color I wanted. Circumference equals the limit as some variable d approaches a. So we're not actually going to get to a, we're just going to approach a. Of 4 times the integral, remember the 4 is because there's 4 quadrants we're looking at, from 0 to d of the square root of 1 plus y prime squared dx. And remember that's just the formula for arc length. So it equals 4 times the integral from 0 to a of the square root of 1 plus y prime squared dx. And if you actually take y prime and plug it in, you get the integral from 0 to a of the square root of 1 plus b squared x squared over a squared times a squared minus x squared. A squared minus x squared. There we go. Dx. And again, that just comes from taking the derivative of that formula up there. Y equals b over a times the square root of a squared minus x squared. So that's where we got this, and it was squared. So we can use trig substitution. If you let x equal a sine of theta, I'm going to need a little bit more room, so let me erase some of this stuff. If you let x equal a sine of theta, then I can plug it into this equation, and I get that the circumference is equal to 4 from 0 to pi over 2. from 0 to pi over 2 of 1 plus, the square root, sorry. The square root of 1 plus b squared sine squared theta over a squared cosine squared theta times a, let me erase some of this over here, cosine theta d theta. Now, if you're anything like me, you're wondering where in the world they got that from, so let me show you a picture of how I worked it out. So, you can see here that all I did was I plugged in what they set x equal to. So if you look back up at the original work we had, right before we used the trig substitution, we had the square root of 1 plus b squared x squared. So I just plugged in this for x squared, since that's what they told me that x was, divided by a squared times a squared minus x squared. So I have a squared times a squared minus, and this is x squared again, so I put that in again. For dx, I had to use the u substitution technically, so we're using x equal to a sine theta. So it's kind of like a weird u substitution, but oops. My bad. Let's see if I can get that picture back. There we go. So if x is equal to a sine of theta, that means that dx, if you take the derivative of that, is equal to a cosine theta d theta. So that's where they got this from, the a cosine theta d theta. And then from there, they simplified it a little bit. So the a squareds canceled out, so they got rid of those. So we had b squared over sine squared theta. And the bottom, we had a squared times, because you can factor out that a squared times 1 minus sine squared theta. And that is cosine squared theta. So you can see that this is where they got that, what was inside of the integral, which they have right here. And then the last thing you might be wondering is where they got the integral from 0 to pi over 2. So if you look over here, sorry, I didn't mean to erase all that stuff up there. If you look over here, if you set x equal to 0 up here, 0 divided by a is 0, so sine of theta equaling 0 only happens at theta equals 0, or in our case, I should say happens at theta equals 0. And if you set x equal to a, like the upper integral was, if you have a for x, that would be a divided by a, which is 1, and sine theta equals 1 at theta equals pi over 2. So that's where they got the integrals, or the new limits, I should say, on this piece. So, let's go from here. Let me see if I can erase some of this stuff. So I can just go back to where we started. Oop, there we go. Alright, perfect. So, from here what we're going to do is we are going to combine everything down into a single fraction if we can do so. So, what I'm going to do is this. I have 4 times the integral. I'm not going to write the 0 to pi over 2 for a bit. If I want to cancel out one of these a's with one of these a's, and one of these cosines with one of these cosines, I can do that. So I have 1 plus b squared sine squared theta over a cosine theta. And from here, if I want to get these to be, d theta, by the way. From here, I can say that I can get a common denominator of a cosine theta. So I have a cosine theta plus b squared sine squared theta all over a cosine theta d theta. My bad, I kind of led you guys a little bit astray. So let's backtrack just a little bit. If I backtrack, sorry, I backtracked just a lot. Hopefully you guys caught my mistake for me before I did, but if not, we'll have to talk about that. I accidentally made the mistake of, for some reason, thinking that a cosine theta was underneath the square root with this, which it's not. So I'm actually not able to multiply or cancel out those terms. So here's how we're going to do it instead. So I have 4 times the integral. I can first get a like term, or I should say combine those two terms. So I'm going to multiply 1 to get a common denominator. So a squared cosine squared theta plus b squared sine squared theta over a squared cosine squared theta times a cosine theta d theta. So now this down here is a perfect square, so I can actually factor that out. So I get 4 times the integral of 1 over a cosine theta times the square root of a squared cosine squared theta plus b squared sine squared theta times a cosine theta d theta. And now these will cancel. So this one here is going to cancel with this one here, which is perfect. So I have 4 times the integral of the square root of a squared cosine squared theta plus b squared sine squared theta d theta. So what I can do from here is I can actually turn my cosine squared theta back into a 1 minus sine squared theta. So this is 4 times the integral of a squared times 1 minus sine squared theta. That way I only have sines in here. And so again, the reason for doing that is that I can distribute that a squared. So I get 4 times the integral of the square root of a squared minus a squared sine squared theta plus b squared sine squared theta d theta. And I'll erase some stuff again to make some more room. So from there I can group together the sine squared thetas. So I have 4 times the integral of the square root of a squared minus b squared times sine squared theta d theta. Alright. And then last but not least, remember that we learned that E is equal to C over A. So therefore E squared is equal to C squared over A squared. And in this case, we know that C squared is equal to A squared minus B squared. So this is A squared minus B squared, over A squared. So if we see that, you can actually rewrite this integral. And again, in the book, they kind of take a few steps, or a few jumps, I should say. So let me kind of walk you guys along. So I'm going to use this piece and this piece here. This piece and this piece here. So if I multiply the a squared over the other side, I get e squared a squared equals a squared minus b squared, which I see right here, a squared minus b squared. So I'm going to substitute that e squared a squared in there. So this is 4 times the integral from 0 to 2 pi, or pi over 2, sorry, times the square root of a squared minus e squared a squared sine squared theta d theta. And I can factor out an a squared from all of that, and I can actually take the square root of that a squared since it's under a square root. So I get a times the square root of 1 minus e squared sine squared theta d theta. And last but not least, if you want to see it written like they do up at the top again, how they asked us to prove it, if you bring that a out front, you get 4a times 0 to pi over 2, and again a is just a constant, so that's why it's okay for us to pull it out. 1 minus e squared sine squared theta d theta. So that problem was kind of long, it was kind of confusing. The book jumps a few steps in multiple places, so it's helpful to look at it laid out like this. We are already kind of long in this video, we're up to 25 minutes already, and we still have 3 more examples left, so I'm actually not going to go over those with you. They're pretty easy, so look at example number 6 on page 643. If you have questions, you can let me know, but I don't think you should have too much difficulty with that one. Look at example 7 on page 645. That one's definitely doable. I think you guys would have no issue with that one. And then take a look at example number 8 on page 646 as well. That one shouldn't be too difficult if you just read through the directions as well. And I'll assign you guys some homework problems, and you guys can let me know if you have questions on those.